Let me review lecture 22 before we go to lecture 23. So in lecture 22, we learned about a reservoir. A reservoir is a very hypothetical space, or I would say a thermodynamic space. Okay, space that has really gigantic heat capacity. So the reservoir doesn't change the temperature. So temperature does not change in a reservoir, even though there is a heat transfer in or heat transfer out. Now, when you talk about the thermodynamic cycles, we have two cases of thermodynamic cycles. One is heat engine. The second one is refrigeration and heat pump. Okay. Now, heat engine needs certain heat input to make work output. So the whole purpose of having heat engine is to get certain power out. Compared to heat engine, the refrigeration or heat pump wants to get certain heat out or put certain heat in to system by applying certain work to the thermodynamic cycle. So heat engine is in opposite purpose and opposite kind of direction with against the refrigeration and heat pump. Now for heat engine and in general heat thermodynamic cycle, we need three very key systems or components. One is high temperature for heat engine. One is high temperature heat source and low temperature heat sink. And now the heat engine is placed in between to get certain heat from the heat source to heat engine. And from this heat input, we do certain net work to get this work out. And the remaining portion, after doing work, should be rejected in terms of heat to low temperature heat sink. Now, in order to describe the performance of heat engine, we need to think about two perspectives. The first one is how much we can make work out from this system. And by applying the first law of thermodynamics, the net work out should be balanced with the difference between the heat input to the system minus heat rejection from the thermodynamic cycle, heat engine. And now, the second perspective we always have to think about is how efficient your heat engine is. And in order to measure that efficient use of heat engine, we have to define the thermodynamic or thermal efficiency, which is defined as desired output. Now, for the heat engine case, desired output is work net out divided by required input. For heat engine, the required input should be heat input to the heat engine. So now by applying the first law of thermodynamics to the equation of W net out, then we can get the thermal efficiency expressed in terms of 1 minus Q out divided by Q in. Then how about refrigeration? Now we still need three components. One is now warm environment. In that case, it should be acting as a heat sink though. And now we have cold refrigerated space at TL. So that can be kind of heat source. Now we have a refrigerator or heat pump cycle placed in between. So what it does is by applying certain net work in to the cycle, we can take a certain amount of heat out from the cold refrigerated space. Now the example of that space can be the kind of food compartment of your refrigerator or inside a house, when you try to cool your house down using the air conditioner. And now we have this much of the heat taken out from the space to cool it down. And now by running the refrigeration or heat pump cycle, by applying this amount of work in, we take heat QH out and dump it to the environment, in the case warm. Okay? If we want to use this thermodynamic cycle for refrigeration, your focus should be more on cold refrigerator space, and your desired output should be QL. Now, if you want to use the same cycle for heat pump, then what your purpose is to put certain heat to your space that needs to be warmed. Now, in the case, the desired output should be QH. And required input to run that cycle is W net in. Now, by applying the first law of thermodynamics, which is energy balance, the energy input W net in and QL should be summed to make QH. Or in other words, the amount of work that we need to put into run the refrigeration or heat pump cycle should be balanced with a difference between QH, the amount of heat that needs to be dumped out, minus QL, that needs to be heat that is taken from the cooled space. Now, we also can define the similar concept as efficiency for refrigeration or heat pump, but in the case, instead of using efficiency, we call that as COP, or the coefficient of performance. Now, COP for refrigeration, again, is defined by desired output minus divided by required input. So for the refrigeration cycle, the desired output should be the amount of heat QL that is taken from the space to be cooled. And now the required input should be your W net in. In that case, it can be balanced as QH minus QL. Same way, we can define the COP for heat pump as the desired output, which in this case is QH, divided by required input, in that case W net in, or QH minus QL.